An understanding of our atmosphere is fundamental to a pilot, since it is not just the air we breathe, but the environment we fly in. This environment can be benign, but equally so very hazardous. There are many physical processes at work within our atmosphere, and these need detailed analysis. These processes will be covered in the following lessons, but for now let us examine what the atmosphere is and what are its main properties. The word atmosphere is defined as being the gaseous envelope surrounding a celestial body. In the case of the Earth, it is the collection of gases that are held around the Earth by gravity. There are well over 20 of these gases, some more abundant than others. We will concentrate on the 4 most abundant gases. By far the most common gas is nitrogen, which accounts for about 78% of the atmosphere. Oxygen, which is essential to sustaining life and the proper functioning of internal combustion engines, makes up 21% of the atmosphere. Just less than 1% is argon, with carbon dioxide making up the rest. There are many more gases making up our atmosphere, but these are found in such small quantities that we regard them as trace gases. These include carbon monoxide, helium, methane, ozone, and hydrogen. However, one of the most important gases with regards to meteorology is water vapor. Without water vapor, there would be no weather. Even though it is found in very small quantities in the atmosphere, it has by far the greatest effect on our weather. Clouds and rain are examples of its liquid state, whereas snow and hail are examples of its solid state. The relative amounts of the gases stay fairly constant up to about 60 kilometers above the Earth. Thereafter, gravitational separation alters the composition of the atmosphere. In order to structure our atmosphere into various segments or layers, there must be a property of the atmosphere that varies with height. The variable we use is temperature. The first of these segments or layers is called the troposphere. This layer is closest to the Earth, and its defining characteristic is the marked decrease in temperature with height through the layer. Because of the effect of gravity, this layer contains over 70% of the total mass of the atmosphere. The altitude where the temperature no longer decreases with height defines the upper part of the troposphere. This upper boundary we call the tropopause. The thickness of the troposphere, and therefore the height of the tropopause, is not constant across the Earth. Over the poles, the height of the tropopause is about 8 kilometers, whereas over the equator, it is about 16 kilometers. The average height is 11 kilometers, or 36,090 feet. This is the case at about 45 degrees latitude. The reason for the height change in the tropopause is simply due to the surface temperature. Where the Earth is warmest, near the equator, the tropopause is at its highest. Looking over the poles, where we have very cold air, you can see the tropopause is at its lowest. We know that temperature decreases with height within the troposphere. Therefore, the further away the tropopause is, the colder it is. Over the equator, the tropopause temperature can be minus 80 degrees Celsius, whereas over the poles, the tropopause temperature is only about minus 40 degrees Celsius. However, the average temperature is approximately minus 56 degrees Celsius, which is common in the mid-latitudes, where the tropopause is approximately 11 kilometers. Having discussed the troposphere and its upper boundary, the tropopause, We will now look at the next layer in the atmosphere, called the stratosphere. This layer is characterized by the lack of any significant change in temperature with height. The stratosphere stops when temperature starts to decrease with height again. At this point, we find the upper boundary to the stratosphere, which is called the stratopause. This is usually found at about 50 kilometers above the surface of the Earth. The temperature of the stratosphere can rise a little in the upper levels due to the presence of ozone gas. But further explanation on this is outside the scope of the learning requirements. Returning to our image of the Earth, you can now see the stratosphere and stratopause. There are several more layers to the atmosphere, but these are outside the learning requirements for the private pilot's license, and will therefore not be considered. Before we leave the structure of the atmosphere, there is an important point to make about the tropopause that is significant to a pilot. We stated that the tropopause was where temperature no longer decreases with height. This causes air to become very stable. In other words, it limits the vertical movement of air. This lack of vertical airflow prevents any further cloud development, and therefore the tropopause signifies the limit of the majority of weather and significant cloud development. For many purposes, such as calibrations of instruments and testing of aircraft, an average state of the atmosphere needs to be represented and modelled. This is called a standard atmosphere. In 1964, the International Civil Aviation Organization, ICAO, defined the properties of this average standard atmosphere, and this is referred to as the ICAO Standard Atmosphere, which is abbreviated to ISA or ISA. However, the model only extends to 32 kilometers, which is about 105,000 feet above mean sea level, so the entire atmosphere is not considered. ISA assumes that at mean sea level, the temperature is 15 degrees Celsius, pressure is 1013.25 hectopascals, and the density is 1.225 kilograms per meter cubed. From mean sea level to 11 kilometers, or 36,090 feet, the temperature decreases by 1.98 degrees Celsius per 1,000 feet, or 0.65 degrees Celsius per 100 meters. From 11 kilometers to 20 kilometers, the temperature remains constant at minus 56.5 degrees Celsius. Notice that at 11 kilometers, the temperature no longer falls with height, and therefore marks the top of the troposphere. You may remember that we called this point the tropopause. The layer above this was called the stratosphere. From 20 kilometers to 32 kilometers, the temperature rises slowly at 0.3 degrees Celsius per 1,000 feet, or 0.1 degrees Celsius per 100 meters. ISA is only one of several types of standard atmosphere, but it is the most recognized and the most familiar of them all. Since all aircraft instruments are calibrated in accordance with ISA, it is essential to know how much the actual atmosphere on a given day differs from ISA. This will help quantify errors and improve the accuracy of the readings from these instruments. The simplest method we use to analyze this difference is by comparing the real temperature to the standard ISA temperature. This comparison gives us what is known as the ISA deviation. In other words, by how much does the real atmosphere deviate from the standard atmosphere? Let's work through an example to help understand this principle. In the diagram, we can see an airfield 1,000 feet above sea level. Remember that in ISA, we stated that mean sea level temperature was 15 degrees Celsius, and then falls by 1.98 degrees Celsius per every 1,000 feet up to 11 kilometers. For simplicity, let's assume it is 2 degrees Celsius per 1,000 feet. Therefore, the temperature at 1,000 feet, according to ISA, should be approximately 13 degrees Celsius. Notice, though, that on the actual day we are considering, the real temperature at 1,000 feet is in fact 20 degrees Celsius, which is much hotter than ISA. A simple calculation tells us that the real atmosphere is 7 degrees Celsius warmer than ISA. The representation of this information is important. The best way to understand it is by reading the ISA deviation backwards. We can say that the real atmosphere is 7 degrees Celsius hotter than ISA. Let's try another example of an ISA deviation exercise. Let's say that on another given day, the real temperature at 10,000 feet is minus 15 degrees Celsius. What is the ISA deviation? Let's first calculate what ISA says the temperature should be at 10,000 feet. ISA says that temperature falls by approximately 2 degrees Celsius per 1,000 feet. So temperature should decrease from sea level to 10,000 feet by 20 degrees Celsius. But remember that the temperature at sea level in ISA is 15 degrees Celsius. So 15 degrees Celsius minus a temperature decrease of 20 degrees Celsius up to 10,000 feet makes the ISA temperature at 10,000 feet minus 5 degrees Celsius. The real temperature is minus 15 degrees Celsius. A simple calculation tells us that the real atmosphere is 10 degrees Celsius colder than ISA. Therefore, the ISA deviation is ISA minus 10. ISA deviation is used widely in meteorology and aviation in general, especially when considering aircraft performance and error corrections for instruments. Because of this, it is important to understand how to calculate ISA deviations. This concludes the lesson. Hopefully we have gained a more detailed view of our atmosphere as a whole. What will follow will be even greater concentration on the individual elements within the atmosphere, such as temperature, density, water vapor, and pressure.